This is an RNZ podcast.
They say life is stranger than fiction.
So it's a big fat ribbon with this huge surface area that allows the entire population of many worlds to inhabit this one ring.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible.
The International Space Station consists of about 200, I think, separate components, and it was put together over many different trips, both by the Americans and the Russians over a period of about 10 years, where everybody took up a new bit of Lego and bolted it onto the space station that was up there.
Or could it? Welcome to Sci-Fi Sci-Fact. I'm Bryan Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. This week's Sci-Fi Sci-Fact is a classic. At least that's what my guest, Dr. Chris Bumby, McDiarmid Institute Principal Investigator and Senior Scientist at the Robertson Research Institute of Victoria University, reckons. And he joins me now to talk about Larry Niven's Ringworld.
The Earth may not be our home forever. Eventually, we may have to leave. What if, instead of finding a potentially habitable exoplanet light years away, we stayed in our solar system and built a habitat so enormous we could never overpopulate it? This is What If, and here's what would happen if we built a ring world in space. Imagine you lived on a ring with a radius of 150 million kilometers encircling the sun. A gigantic artificial world with its own gravity, ecosystem, and atmosphere, big enough for trillions of humans to call home. You'd live on an enormous landmass on the inner side of the ring. The outer shell would protect you and all those trillions of people from the hazards of outer space. How does that sound? Yeah, great. Problem is, assembling such a thing suspended out in the solar system wouldn't be easy.
I have to admit, I have not heard of Ringworld. And I was thinking, is this a Lord of the Rings kind of meets the Terry Pratchett sort of idea of the cosmos, the turtles on their back or whatever it is, the disc world? But I think I'm way off the mark, aren't I?
Well, you're way off the mark, although, interestingly, Terry Pratchett did admit that the Discworld and some of the precursor book he wrote, Strata, was actually a pastiche of the Ringworld, of Larry Niven's Ringworld book.
Really?
So it has been, yes, it's been an extremely influential book through the science fiction over the last 40, 50 years. And I'm reliably informed that the modern video game Halo also has ringworlds that are based on this original idea of Larry Niven back from the 70s. This is a book that was published in 1970, from the golden age of science fiction, when Asimov and Heinlein and Clarke were all publishing heavily as well. But yeah, it's a great book, but sort of based in the space opera type far spacefaring future, where we've got spaceships that can travel with warp drive and in impermeable hulls and all sorts of alien species and all sorts of good fare that you see in science fiction generally. But the basis of this book is about this megastructure, this huge world in the shape of a ring, which encircles a star. And the story goes that our heroes are in a spaceship and they crash into this ring world and have various adventures whilst they're on the world. And eventually they get off the world, even though their spaceship is broken and their warp drive doesn't work. But they can get off by jumping through a hole in the ring and being shot back out into space and then rescued. There's a heck of a lot, actually.
Why
in the
would
book.
they?
It's only 350 pages.
Only 350. Well, I guess that's actually reasonably short, given the length of some of the sci-fi classics. It's shorter than Dune, isn't it? Dune was pretty fat, wasn't it? Yeah. I remember my brother reading
that recently.
Yeah, my brother read Dune, and I was thought, that book's fat. That's big. That's even bigger than Lord of the Rings. How does he do it?
I was reading that recently, fell asleep, and dropped it on my face, and promptly woke up again.
Right, so it's a manufactured. Well, it's not a planet. That's the thing, but it's basically follows as a ring that kind of follows. Say if we could build this ring that went from all the way, followed Earth's orbit all the way around the sun. Okay, our orbit around the sun is an ellipse, not a ring. But if it was, this is the kind of this is the sort of size that we're talking about of this artificial.
That's right.
World.
That's right. You've got it. So the book talks about it being a million miles in diameter. It's an American book in imperial units. So we'll just work in metric. It's at 1.6 million kilometers in diameter. Sorry, I've got that wrong. 300 million kilometers in diameter and 1.6 million kilometers wide. Sorry, got my units the wrong way around. That's right. So it's a big fat ribbon with this huge surface area that allows the entire population of many worlds to inhabit this one ring. And so you can understand why, as a science fiction author, you'd pick an artifact like this.
How did they manage to crash into it? They would have seen it coming, wouldn't they?
Well, yes. So the story goes that this spaceship comes in and that it's a fairly weird looking thing. So they want to go and have a closer look. And as they come in towards the star, they see the ring and they look at the ring, and then they look behind them and they see that as in between the ring and the star, there are a series of what appear to be squares that are also spinning around the ring. And these things turn out to be called shadow squares. And so they're what actually causes day and night on the ring, because if you've just got a star inside a ring, there's no night. So the way that the night is generated in this structure is that they have a series of squares that also spin around the star, and they give you periods of shadow and light on the ring, and then that gives you your day and night. Now, these squares are all roped together with what the book calls shadow square wire, which turns out to be this incredibly thin monomolecular filament that basically is the world's greatest cheese wire. And when they run their spaceship through what they think is a gap between these squares, they hit this wire, all hell breaks loose, and the spaceship eventually crashes into the surface of the Ringworld. And when it does this, it makes 1,000-kilometer long gash through the surface of the Ringworld, but it doesn't damage the material underneath. It leaves this shiny metal sort of gash through the landscape that proceeds a long way around the rim before eventually coming to rest. And so that's where the story on the Ringworld itself starts, is with this crash landing into something that's clearly pretty hard because they've just skidded 1,000 kilometers along it.
Okay. I would assume that the locals would be extremely pissed off about this crash. They've done a lot of damage to the locals' ring.
It takes them a while to find any locals. It's a really, really big structure. So it turns out that where they've crashed, there just aren't any people. And in fact, they then go off on their adventures, and they have to travel many thousands of kilometers before they find anyone. And eventually they find some people who turn out to be human, and the story moves on from there. But I'm much more interested, I have to say, as a scientist, in talking about the structure itself.
I know that's where you want to go, Chris. But I just want to hold you back for a moment, Chris, before we move on into the physics of this thing and whether it could actually exist. Mm-hmm. And that is, look, if you've got a civilization that's so advanced it can create a ring that is basically a world that it extends around a star, a bit like the Earth's orbit. So it's probably, how wide is the thing? Is this ring? Up and down.
So just to repeat my numbers the right way around this time. So we've got something that's 1.6 million kilometers wide and has a diameter of 300 million kilometers. So
so from one side of the ring to the other, you're looking in from, to get to the edge of the ring, and from one edge to the other, 1.6 million kilometers. Mm-hmm. Okay, that's right. Huge.
So that's pretty huge.
I mean, that's further than the distance from here to the moon.
Yes.
In fact, it's about 3 times or 4 times the distance from here to the moon.
It is. It's a vast structure, and in fact, the book talks about the fact that the structure contains all of the material from its host solar system, and it's implied that its host solar system was probably originally our solar system, Earth's solar system. And the only way that can happen, of course, is if you make it really thin.
Yeah.
So it's got this vast surface area, but it's only 30 meters thick. And so we've got this incredible material that forms this ring that's only 30 meters thick, but it extends around this enormous stellar orbit.
You don't want to go drilling holes into it then.
Well, it turns out to be quite hard to do that. They crash a spaceship into it and it just bounces.
Right, okay. Now, before we get into detail, here's my question. Maybe I should wait till the end, but it's too late. It's in my brain now, so I've got to ask it because I might forget it later on. A civilization so advanced it can create this, why would it bother with night and day? Wouldn't you just, we'll just have the sun all the time. If you don't want the sun, we'll build shade. What's this sort of night-day thing? That seems like, I don't know, it's almost a bit twee.
Well, maybe, but I think it's fair to note that human beings themselves require some sort of diurnal schedule in order to not get
but
sick.
if you've evolved to the point where you're building a massive ring that's the size of the Earth's orbit, and actually quite a bit, and it's as wider than the Earth to the Moon, why would you then, but we've got to keep night? Nah, mate. Can't do without night and day.
I can think of at least two other reasons. Okay, I can think of at least two. First, on this ring, they've decided that they've transplanted ecology. And the bit of the ring that we go in the first book, it's Earth-like ecology. So we've got wildlife. Wildlife without night and day also gets really quite messed up. So various animals, trees, plants, all of those sort of things. You're going to need some sort of day-night structure for that. And it's worth noting that these shadow squares don't actually give you perfect day-night. You don't have any twilight. There's no period that you'd have on the Earth, where as we turn away from the Earth and the sun goes low in the sky, we get that sort of dimming of the light and that gradual change. What we have here is it's bright noon and then bang, the edge of the shadow comes across and suddenly it's dark. So it's a very swift changeover. So it's not a perfect day-night by any stretch. But there's one other reason that comes to mind that you might want to do this. And that's because if you've got a ring facing inwards towards a very hot burning ball of gas, which is now emitting heat everywhere, and you don't have any time for the surface to cool down, it's going to get fairly hot. One of the reasons the Earth is the temperature it is because it spends half its time re-irradiating its heat back out into space. So nighttime is actually a cooling mechanism for the Earth. And I think maybe you might need something similar, now I think about it, on the Ringworld to prevent it just getting too hot for everybody to survive.
Right, which brings me, I'll save this one for later. Atmosphere and how you could actually have an atmosphere that stays on the ring. But let's go back.
That's quite important.
Yes,
maybe we
is.
should do that now.
Do you want
that is actually quite important.
But because I thought maybe we should move to the actual structure now. And this massive structure, which has a massive what? Mm-hmm. How much bigger than the Earth in terms of mass is this ring?
I told you not to ask me numbers that I didn't put down.
All right, then I'll read your notes for you, Chris. 2.7 times 10 to the 27 kilograms. Earth is, 6 times 10 to the 24. So it's 450 times bigger than the Earth in mass. Actually, it's a little bit less than I thought it might be. But then you did point out it's very thin. It's only 30 meters from the ring itself is only 30 meters deep. Yeah, that's right. The book talks about it, as I say, being all of the material in the solar system. And if you think about our solar system, a lot of the mass in our solar system is in the big gas giants. Now, they're not actually that dense, but they're pretty big. And so there's a heck of a lot of mass sort of sitting in those systems. I think it is worth noting as well that some of the maths in Larry Niven's book isn't necessarily perfect. And so when you start working out exactly the structure of these things, you end up with numbers that are slightly different to the ones that he might quote at certain points in the book. And I'm sure his get out is, well, I didn't say it was an Earth solar system. I just said it was a solar system. But anyway, that gets you in the broad sort of region of what's going on, and so that's how you can get such a large surface area, of course, right? Given its size, given it's a ring around a star the mass of our sun, and how far is it? Is it about the same distance from the sun as the Earth is? The ring, the inside of the ring.
That's the idea. Yes, it's about 1 astronomical unit.
Okay, right. Okay, and given this, it's got its own gravitational field, I assume. It must have. It's got mass.
Yep.
Wouldn't it and the gravitational field of the sun rip it apart?
Well, so this is where things get interesting. So gravity in a ring is not the same as gravity on a planet. So there's a few things that we need to bear in mind here. Firstly, we like our gravity to act down. Generally, when we're standing on a planet, we'd like to be pulled towards the center of the planet. That's problematic if there's only 30 meters of material below you, pulling you down, because that means that all of the rest of the material is around you and above you and is actually pulling you in the other direction. So that means that, to all intents and purposes, there's zero gravity on this when you're standing on the surface of this ring. But we need people to stay on the surface, and as you pointed out a minute ago, we need the atmosphere to stay on the surface of this ring as well. So the way it deals with that is we spin it up. It's the classic old bucket on the end of a string experiment, right? Where we spin the whole thing around, and then we've got a big old centrifugal force that pins everything to the inner surface of this ring.
Or Billy
Now
T.
we've got artificial gravity.
Have you ever made Billy T, Chris?
I have no idea what
so
you're
that's
talking
what,
about.
okay, so this is when you're out camping and you get your tea, loose tea leaves, and you get your billy, your little, and you've got it on a handle and you swing it around like nobody's business. And this a extra centrifugal force pushes the tea to the bottom of the billy, and in doing so, it also releases the tea once you run out of the tea into the water, and there you are. You got your billy tea.
Exactly. So that's the basic premise here. Now, we probably should talk about this atmosphere.
Thanks for indulging me there, earlier. Chris, by the way.
That's all right. That's all right. So we've got this atmosphere on this ring going round and round and round. Now, that's all well and good. The atmosphere is now being pushed against the ring, but atmospheres are fluids and they can flow. And so if it was just a ring, they'd just flow off the edge of the ring, and then we'd have no atmosphere left. So in order to keep this atmosphere in, on either side of the ring, they've got these enormous mountain ranges which form rim walls. And these walls are high. They're 1,600 kilometers high. That's seriously high mountains. They extend miles out of the atmosphere. And so what we actually have is this sort of trench in the inside. The ring forms a trench with these two channels on either side in the shape of the inner ring. So when we spin the atmosphere, and it gets stuck in that trench and stays there and doesn't come out.
Is that plausible?
Does that answer your previous question?
Is that plausible?
Yeah, that's relatively plausible. If you think about how the atmosphere stays on the Earth, actually, that's about as plausible as the atmosphere is staying on the Earth. On the Earth, right, what we've got is a big ball spinning round, and we've got a gravitational force that is holding their atmosphere to the Earth. But at some point at the edge of the atmosphere, we've got space.
What will the atmosphere be like? Say you're walking along the ring and you come to the wall. There you are at the wall, straight up, 1.6 million kilometers now. What kind of atmospheric forces are going to be at that point where the rim of the ring meets the wall of the ring?
I don't think it's a sheer wall. I think it's more of a mountain range that moves up over time. And but you're right, it's going to get windy. Somewhere in there it's going to be quite windy. But the entire point of this planet really is that the denizens, that the people who inhabit the Ringworld, stay on the Ringworld and don't get involved in the engineering of the world itself. There's a separate class of species called the Ringworld engineers who originally built this place and live outside.
But Chris, you haven't really answered my question yet. Would this thing hold together? It wouldn't.
No.
Why not?
Because, well, there's a few different challenges. Actually, there's a number of reasons why the Ringworld has problems. And before we even start talking about would it hold together, we should probably talk about would the star stay where it's supposed to stay? Because the answer to that is also no. But what we've got is this big ring that's spinning really fast. And so as it's spinning really fast, in order to generate this gravitational force, it's equal to 9.8 newtons per kilogram, right? That's gravitational force. And it's huge. It turns out that the velocity on the rim is about 1,600 kilometers a second. And it's doing this huge orbit. But that's really quite fast. And so what we have now is, as well as the force acting out on the ring, that causes tension all the way around the ring. And this is called hoop stress, this tension. And it's quite well known, and you see it in all sorts of other systems down at quite small levels. So the system that I'm most familiar with is for pressure cylinders for gas storage, so compressed gas, where you need to be able to make sure that the pressure of the gas you put inside your cylinder doesn't make your cylinder explode. And so you can work out what the stress is that goes around the cylinder. If you use the same maths to do that for the Ringworld, you can work out what the stress must be in this 30-meter thick band of whatever this ring floor material is that holds the whole thing together when it's spinning at 1,600 kilometers a second. And it's a big number. It's a stupidly big number. It's actually such a big number that it is about 5 million times the strength of steel. That makes the number that's approaching the same order of magnitude as the forces that hold together nuclei inside an atom.
Right.
So there just is no material possibly conceivable that could achieve that sort of strength.
In fact, didn't a bunch of Harvard physics students point this out at some kind of Comic-Con conference back in the day with placards?
Oh, well, that was a slightly different problem. So that's the other problem. So firstly, we've got this ridiculously fast spinning ring that's going to pull itself apart. But the other issue we've got comes back to this idea of what is the gravity inside a ring. And so a ring is a rigid object. So it doesn't behave in orbit in the same way that a planet would around a star. And so if we put a star at the center of a solar system and we get a planet like the one we live on and we send it off at a velocity, it'll go round and round in an ellipse or a circle or whatever we set it off originally to do. And that's fine. And the reason for that is that the star exerts a gravitational force on the planet and the planet exerts a gravitational force on the star. And so they're connected, they're attracted to each other in a way that gives you this centripetal force that gets it to go round and round. If we've got a ring, there's a gravitational force of attraction happening between every point on the ring and the star. But there's also the fact that the points on the ring are all rigidly connected to each other. And so what that means is when you pull on one bit of the ring, it makes the whole bit of the ring move, just like a giant hula hoop. And so we all know that you can do the hula with the hula hoop, and it's all about how you make things go around.
But you've got to have a body inside the hula hoop swinging its hips the right way. And the ring doesn't have that. It's only got a star.
Well, it's got a star, that's right. And so that star, if it's right at the center of the ring, the star experiences zero gravitational force from the ring. There is a 0 point right in the middle of the ring. And that's because effectively all points on the ring are pulling away from that point equally. Yeah. So there's actually no force there at all. The problem is that if it perturbs even a tiny little bit in one direction, suddenly the gravitational force now attracts it more in the direction it's gone towards that bit of the ring than to the bits of the ring it's further away. And so what that means is that the star wants to stick to somewhere on the ring. It does not want to stay in the middle. It's kind of like trying to balance a snooker ball or a pool ball on a knife blade. In principle, there is a minimum there, but in practice, trying to get it there, the moment there's any perturbation, it's going to fall off. And so it only takes a few specks of interstellar dust or some minor asteroid.
Or somebody crashing into it.
Somebody crashing into it. And that star is on its way.
The star would then crash into the ring, or the ring would crash into the star.
Ring.
It doesn't really matter, one or the other. Same result. That's
right. I mean, that's right. You could possibly imagine some slightly eccentric orbit where maybe the star is able to sort of do a toroidal type orbit around the ring itself. But in all honesty, I don't think that's very likely. I think they're going to crash.
But then the ring's going to be facing the wrong way, and they're all going to be in darkness.
Well, they're all going to be incinerated is what they're going to be. And
is that what the physics students were complaining about at the Comic-Con back in the day?
That's right. That's right. So this book came out in 1970, and it was kind of the early days of the Comic-Con conferences and whatever else. And it attracted a lot of interest because physicists like me think this is a pretty cool idea. But they take their science fiction quite seriously. And so a number of people pointed out quite quickly that we have a fundamental mechanics issue here. And as a result, they went along to this Comic-Con, and it was actually a bunch of MIT physics students and postgraduate students who brought their placards, and they picketed Larry Niven and said, "You've made a mistake." So he got quite embarrassed about this.
Really? Were they angry?
Oh, angry might be overstating it, but very clear. Anyway, Niven was quite embarrassed about this, and so in the end, he ended up writing a complete sequel to Ringworld, which was published 10 years later, called The Ringworld Engineers, in which he revealed that actually on the underside of the ring, where they hadn't had a proper look in the first novel, there were these thrusters, and the thrusters were there to keep it all centered up so that the star stayed exactly at that zero gravitational point in the middle of the ring, and therefore never got into a point where it got into a runaway perturbation.
Yeah, right. Okay. They'd have to be very smart, wouldn't they? Because if you thrust at the wrong point at the wrong time, you'll be creating a perturbation, won't you?
Oh, well, you will, but you've got a bit of time, right? It's whatever it is. 150 million kilometers away, so you've got time to reverse. What you need is really good sensors so that you can hold it perfectly there in the right point. I agree. The closer you let that star get to the ring, of course, the more energy you need to use to get it back into the center of the ring. So you want to be as good as possible as keeping it perfectly in the center to minimize your energy consumption.
If you had energy that sufficient energy to run those thrusters, could you create a stable ring world?
Well, we can do the first bit, right? We can stop it crashing into the star. So that's a good start. But we haven't solved this problem about we've got this enormous forces acting on the ring, which are going to rip
on the
it
material
apart.
itself, the 30-meter deep
that's
ring.
Right.
It's still going to fall apart.
It's going to fall apart. And so that's fundamentally a problem with just how huge this ring is. And so the only real way we could start thinking about how could we make one of these things that didn't do that is just to make it a bit smaller. And so we can think about this. And if we made it out of, say, titanium aerospace alloy, which is a nice, lightweight, high-strength alloy that at least we know about and we can get some numbers from, then we can work out that we could, in principle, make a ring world that had a diameter of about 44 kilometers from one side to the other. Now, that's still pretty big. But the problem now is we've got to put a star in the middle. And the radius of our sun is about 700,000 kilometers. So we're a lot smaller than our star. So we've just incinerated everything.
Yeah, we're fried.
And so
we're
that's
toast.
the challenge now. Yeah, we are toast. And so we can think about, well, okay, maybe if we're not using titanium, what else could we make this out of that conceivably might be a bit stronger and let us get a bit bigger? It might be monofilament carbon nanotube fibers. So these are single molecule fibers, right? So all of the carbon atoms are arranged in a tube, and they're all covalently bonded to each other, and it goes on in a long chain. And so originally we were able to make these things that were sort of the width of a human hair long and whatever else. But over time, people have got better, and now you can make them that are sort of centimeters long and up to half a meter long, which is incredible, actually, to make a single molecule that's half a meter long. That's amazing. But it's still a lot shorter than the sort of lengths we're talking about here. But nonetheless, we're in the future. Let's assume that somebody's figured out the perfect way to make monomolecular carbon nanotube fibers.
If we were dealing with a dwarf star, that's burnt itself out and still is exuding some energy, and this could be a solution. Say if your star is dying, then you could create that ring that's smaller, and it would be it wouldn't matter that it's so close, because now we've got a much smaller and colder star.
Well,
are there stars that are small
44
enough
kilometers is still pretty small, isn't
okay,
it?
there's no star that's small enough that this ring that is physically possible could go around and we'd get the energy we need to survive.
I think we'd have to have a bit of a think about that. I think you're going to end up with something that looks a bit more like either some sort of artificially trapped fusion center, or maybe you can do something cute with a neutron star that somehow traps enough. The problem is that most of these collapsed stars don't actually emit very much energy. So you need that solar energy to keep your world going, right? You need it to grow your plants, to provide all the energy that keeps your life sustained and the food for the people on the planet. So the problem we've got is that, and as I said, with titanium, we've got a diameter of about 44 kilometers. With carbon nanotubes, we can push it out to about 6,000 kilometers, but we're still 100 times less, smaller diameter than our star itself. And you're now challenging my astronomy to whether it is possible to get a star that small.
What if it was a neutron star?
Not one that gives you enough heat.
No, neutron stars can be really small. Now,
but they're pretty cold, aren't they?
They don't release enough energy. I thought they actually released a lot of gamma radiation, dangerous radiation.
That
would be the
fun.
problem.
That could well be a problem. Oh, here we go. Yes. So no, neutron stars, we may be able to fit one in there. They've also got very, very large gravitational fields.
Yes, I was
so
thinking
that
about
business
that.
about being unstable might become a lot more complicated to deal with now, because you only need to get a tiny amount off, and your gravitational forces are now even a lot bigger than they were before. So your time to react with those thrusters and get everything back centralized has become a lot smaller. But maybe we could consider some way that we get a neutron star that actually gives out some heat. And I think we'd need to think a bit carefully about how that's done. You might need to shoot stuff into it.
And we might also have to adapt so that we can harvest this energy from the neutron star in a way that it's usable to us, and also protect us from whatever dangerous radiation might be coming out of the neutron star. But let's assume, Chris, that we've got a star that's small enough that we can get that smaller ring, because the one that Mr. Niven wrote about is too big, and really you'd have to change the laws of physics. You'd have to change them in order for us to have a ring that size. So let's assume we can create the ring you've talked about using the best nanotechnology we have, the strongest fibers that we currently know how to make, in theory. Around a star that's small enough to fit inside. It's probably a neutron star. We've dealt with the issue of radiation from the neutron star and harvesting of energy from it. Then we got this issue, and that is the energy we need, the technology we need to even build the thing in the first place.
Well, that's right. So, and again, it depends how big our Ringworld is and where we are in that context. But what we have here, ultimately, when we start spinning this, is a giant flywheel. Now, flywheels have been used actually for hundreds of years to store energy, and you need energy to spin them up. And the bigger it is, and the heavier it is, and the faster it's going, the more energy you need to spin them up. So if we go back to Niven's original Ringworld, at that full 300 million kilometer diameter, we end up with a number that's just staggeringly huge. It's 2 times 10 to the 28 joules. Now, that's such a huge number that I had to go and have a think about other ways of thinking about how to understand that. Total global energy consumption, the total energy consumption on Earth today is 6 times 10 to the 20 joules per annum. So that means it would take 40 million years at current global energy consumption, if we used all of the energy on the Earth to do nothing else but spin this world up from stationary to this spinning high energy state, it would take 40 million years to do that. That's clearly not practical at our current level of technological development.
But we do have a huge source of energy just down the road, 8.5 light minutes from us, or thereabouts. How much energy is coming out of the sun?
So, well, the sun's pretty good, right? The sun's getting up there. The sun's about 3 times 10 to the 26 watts. So 3 times 10 to the 26 joules per second. So that's actually not too bad. That suggests that it takes about a minute or so if we could harness all of that star power, bearing in mind it's currently coming out as photons, and a few of it, mainly photons. If we could turn that into mechanical power and turn all of it into mechanical power, we'd only need a few minutes of all of that power to do that. Challenge is, how do we harness all of the power from a star? Because most of it's going out in directions that don't land on the Earth, right? The Earth is a relatively small part of the full sphere, that the full solid angle we talk about that the star is emitting over. And so this kind of brings us back full circle, because Larry Niven's original book was all about a megastructure that was based on a structure called a Dyson sphere. And a Dyson sphere was actually invented by the physicist Freeman Dyson, who was talking about ways that you might be able to look for astronomical signatures of alien races. And he said, well, an alien race would need to be able to, if it was sufficiently advanced, would need to want to harness all of the energy from its star. And so it would draw this big sphere around a star. It would encapsulate the whole star, not in a ring, but in a sphere. And then it would put photovoltaic cells or some other form of energy converting panels on the inside surfaces of that sphere, so that it could capture all of that energy and use it for whatever purposes it needed. And so that's what we're talking about here, really. The Ringworld is kind of just the middle ring of that sphere.
Chris, what would the sphere be made of?
Well, we're back to the same problem. So firstly, it's not stable. So spheres have the same problem as rings. They're not stable if you put a mass in the middle of them. In fact, there's no gravitational field at all inside a sphere, so that the star will just wander off wherever it wants to be. And then you've got to decide, well, how hot is it and how fast is it moving? The one advantage the sphere has over a ring world is we don't necessarily need gravity in our Dyson sphere, so we don't have to spin it anywhere near as fast. So we can reduce significantly the forces that are acting on it. But you're probably going to be pretty hot because you want to get close enough to the star that you don't have to make it massive. All of which is serious challenge. But
how would we find one? Say they exist. Well, here's a couple. Let's go with that one first. Say they exist. You'd be looking for gravitational evidence of a star, but if it's inside a Dyson sphere, we wouldn't see any energy because no energy is going to escape from it.
Exactly. So that's one way you could look for it. Actually, there's another way you can look for it as well, because this business about them not being stable is quite a big deal. But what you can do is you can break them up, much like the shadow squares in the ring world. If you break them up into smaller bits, you can actually put an array of orbiting objects around the star. So you won't necessarily capture all of the emitted radiation from the star, but you can get a decent fraction of it. And what we'd see in that case is a star which has this very periodically varying luminescence as something passed across it regularly. And in fact, there was quite an interesting news story a few years ago about exactly this, where astronomers had found a star that was behaving very oddly, and we weren't at all sure what was actually going on. Now, sadly, I think eventually people decided it was probably a pulsar. But the original behavior was quite strange and took a while for people to decide that it genuinely wasn't a Dyson sphere that they'd spotted.
Obviously, large planets that orbit that star coming between us and that star would also affect luminosity, wouldn't they?
That's right, but they're only going to turn up every once in a while. The thing about planets is they have very big orbits, and they spend most of their time away from the star, either behind it or to one side of it. A Dyson sphere, because we want to capture a decent amount of this energy, we want several of these orbiting objects to be coming past any line of sight quite frequently, so that we're capturing a significant amount of that radiation, because any radiation that we can see on Earth is radiation that hasn't been captured, right? So if we're going to try and capture a significant portion of this, we need to be interrupting that radiation quite frequently.
Is that idea of an array of various objects orbiting a star, capturing a significant amount of its energy, is that physically possible?
It is. You do have a few issues. So we've got a many body problem here, right? The moment we put extra things into our orbits, we have the potential for them to interact with each other. But I would invite you to consider that we live on a planet in a solar system which has quite a lot of things orbiting a star, and it's been stable for quite a long time. So it's possible to find quite stable orbits for these sort of objects, and you can add quite a lot of objects into that array, as long as they're not a rigid body, as long as they're not actually connected to each other. The problems start once you make them a rigid body, because then they're interacting with each other rigidly, as opposed to purely by a 1/r² gravitational interaction.
Now, if you had an array that was capturing enough energy from your star, then could you use the energy to spin your ring and give yourself a ring world? Of course, the problem we have is that we've already decided that the star is probably going to have to be something quite small, like a neutron star. I don't know if you're going to be able to capture enough energy from a neutron star to power your ring. So I think
you're going to need to use a different star. Yeah, a different star to generate the power from whatever you're putting in the center.
Say you're in a binary. Say you're in a binary star system, and you've got your neutron star, you've got the ring around, and then you've got another star more like the yellow dwarf star that we've got, looking after the array, and then it sends all that stuff off to the ring. Although then you'd say, well, why would you bother living next to a neutron star when you've got a perfectly good sun? I mean, why would you do that? The sun's a nice star, isn't it? It's a beautiful star. Yeah. There's another thing you wanted to talk about, the Kardashev scale.
That's right. So the Kardashev scale is actually all about this concept that as species move through stages of technological advancement, they use more energy. So the ring world is perhaps a slightly obscure and maybe slightly non-core use of energy. But the idea that as you become spacefaring, as you move to higher levels of ability to move around the cosmos or to just influence your own solar system, you're going to need more energy. It is quite well accepted. Certainly takes a lot of energy to get in a spaceship and get off the Earth, and it would take even more energy to move to another star system. And so the Kardashev scale basically talks about three different types of civilization. The first civilization, which is a type 1 civilization, is a planetary civilization. So basically that's talking about a society that is largely based on a planet, and it's able to harvest all of the energy available from the star that falls on the planet, basically. So effectively equivalent to the total insolation on the planet. And then a type 2 civilization is a planet, is the sort of civilization that has a Dyson sphere. So it's able to harvest all of the energy, equivalent amount of energy for all of the energy coming out of a single star. And so at this point, clearly they're already moving into sort of societal structures where you're able to move around your solar system, and you're starting to move out, probably outside of your solar system, into other stellar units as well. And then Kardashev went further and said, well, maybe we could have a type 3 civilization, which wasn't just based in a single solar system, was actually able to harvest energy equivalent to that available on a galactic scale, on the local galaxy scale. So that has to be some sort of society that's spread through the stars and able to harvest energy across all of these different stars. Now, whether or not it's actually possible to achieve a type 3 civilization, I think is a moot point. Even type 2 seems like a big ask, and you'd certainly need a type 2 civilization to build a ring world. What's particularly interesting is to think about where we are today. Right?
Where are we today? Where would we sit on that scale right now?
Well, we're not on the scale. It's the short answer. We're nowhere close. We're about 0.7, and that. Even that, of course, is made up from our current global energy balance, which includes an awful lot of fossil fuels and other depletable fuels. So quite apart from the climate change issues associated with them, because they're depletable and because we're now talking about really long timescales, the amount of time necessary to grow your ability to consume power is much, much longer than the amount of resource available. Right? So the amount of coal or oil left available. It's estimated it will probably take, at the current rate of growth, another 350 years for humankind to maybe approach a type 1 civilization. Now, we're going to run out of oil and coal well before then. So in order to get to type 1, we are going to have to transfer from current power and energy generating methods around the world into one that's generated by renewables and also probably by nuclear fusion. I think realistically, the only way we'd ever get to a type 1 is by actually being able to generate nuclear fusion. So the reactions that happen inside the sun, and to be able to do them reinforceably on our planet here before we even start thinking about going off to other solar systems or whatever else in a tokamak or some other type of fusion reactor.
It seems to me to be another argument for the, if I've got it right, the Fermi paradox, which is if there are alien civilizations out there, why can't we see them? Because when you talk about the possibility of a type 1 or type 2 civilization, as I said earlier, you would have thought they would be able to spot this because you would see less energy coming from a star than you would expect. And apart from that case that you talked about before, which is, as you said, probably a pulsar, we have not found anything like that yet in the infinity of space.
We haven't been looking for very long, to be fair. We really have only been looking for a fairly short period of time, a few decades properly. And some of these stars are a long way away. So we do have a lag time of millions of years or more in some cases, which is a fairly big margin of error. And the universe itself is pretty big. Even our galaxy is pretty big. So I think those are all reasons to be cautious in drawing any specific conclusions. But I think I have to agree with you, actually. Any type 3 civilization out there is going to be making some pretty big impacts on the galaxies in its local environment, and you'd certainly expect to be able to see them. Maybe a type 1, not so much. A type 1 could technically still be sitting on its own planet and only doing little zips out to its local moons and maybe a couple of local planets a bit further out in the solar system. And maybe that wouldn't necessarily have such an obvious impact that to be able to be measured around the rest of the world. It's an ongoing debate, and there's a big community searching for extraterrestrial intelligence, the SETI community, who do all sorts of interesting stuff, right? They do a lot of interesting astronomy, kind of because if you go out looking for curious things, you go and find curious things. And
the cosmos is full of those, whether they are the result of civilization or not.
Absolutely.
Finally, Chris, what if we shrunk the whole Ringworld thing to a smaller scale, maybe 100 meters across, or maybe a few kilometers across, or maybe a few hundred, and use the centrifugal force to create gravity inside a spacecraft or some kind of space station? That seems plausible and even desirable.
That's totally plausible, and there's a lot of science fiction in particular that's talked about these sort of rotating systems, everything from Arthur C. Clarke's Islands in the Sky to various other structures that are out there. I'm not actually sure, but I have a suspicion there might be some parts of the International Space Station, very small bits that are only a few meters across, that have some angular momentum to impart some artificial gravity effectively in those areas. And it's a very sensible and simple way to do that. The reason being that, just like gravity, centrifugal force is proportional to mass. So the heavier you are, the more force you have holding you down. So you have exactly the same effect as you have with gravity, where you have this constant acceleration regardless of how heavy you are, which means it feels like gravity and it doesn't feel like someone just pulling you in one direction.
And what's the largest perhaps we could build at the moment with our current technology? Say we wanted to.
So if we go back to that titanium aerospace alloy, I think we're back at about 44-kilometer diameter. Now, I am fairly sure there's not enough titanium in the world, at least titanium alloy, because it doesn't just contain titanium, that sort of alloy. It also has vanadium and aluminium in it, and the vanadium in particular is quite scarce. I'm fairly sure there isn't actually enough of that in the world to make something that big. But let's assume we can go and mine some asteroids somewhere around in the solar system and find enough material. Then something around that sort of 40 to 50 kilometers diameter is just about plausible. Bearing in mind that's already absolutely massive, and the energy required to put that together would be becoming implausibly huge. But the materials, in principle, could take it.
But it might just be what we need if we wanted to go for really long distance space voyages that take thousands of years, perhaps.
Yes, absolutely. These sort of I've forgotten the name now, but science fiction again is full of these sort of colony ships where whole worlds exist on a ship, and you go through multiple generations before you arrive at a star somewhere else. And yeah, they need to be big. Of course, you can't build one of those on a planet. So you're going to already be committing to building these things in space, because it's too big to get off the planet. The gravitational forces and the thrust forces associated with trying to reach escape velocity are going to pull it apart. So you're already into this idea about the energy required to move stuff off the planet into orbit and then assemble it into structures. But we've started doing this. The International Space Station it consists of about 200, I think, separate components, and it was put together over many, many different trips, both by the Americans and the Russians, over a period of about 10 years, where everybody took up a new bit of Lego and bolted it onto the space station that was up there. So we're on that route already. It's just a question of what happens next and how long it takes to get there.
Thanks for listening to this episode of Sci-Fi Sci-Fact, hosted by me, Bryan Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci-Fi Sci-Fact on the RNZ podcast page. RNZ's podcasts are also available on Apple Podcasts, Spotify, and iHeartRadio, or pretty much wherever you find your podcasts. And make sure to follow us so you don't miss out on any new episodes.